Now, let's begin with our first presentation. Please join me in welcoming Mengye, professor at New York University. He will deliver a presentation titled The Always Learning Machine. Please give him a warm round of applause.
Thanks for the introduction. Thanks for having me here. It's very excited to give this talk. So let me begin by tell you about the two potential paradigms of AI. I mean, one is already pretty much realized. I call it the freighter paradigm, where you build a tens of thousands tons of cargo ship, and this is the model, and you put all kinds of data as containers on the ship. Okay, so the data come from the internet, comes from human demonstrations, come from engineering, all kinds of post-training tasks and rewards, and then keep refining it so that it contains everything that we can possibly ship in a container. Okay, so we have seen a lot of success with this paradigm, but there could be another potential alternative, which I call it the sailor. The sailor isn't nearly as big as the freighter, but it allows you to sail to anywhere in the open sea. Okay, so you will grab resources as you need, visiting different islands, and even potentially build your own sail and your own deck using the resource you can get. Okay, so the second type is more of a kind of aspiration that inspires our research more than it's something that's already realized. And we have no idea right now how to realize it, right? So, the freighter is our today's big frontier AI models, and the sailor is the always learning machine that I'd like to share today. So if you imagine today, if you build an AI agent, what does it like to be living from its own world, from its own experience? Imagine that you wake up, today is 10 years later, 2036, okay? And you wake up, you're a helpful AI agent, and this is what happened a week ago, this is what happened yesterday, and what would you like to do next, right? It doesn't feel very real in this AI agent. The memories are all scattered in your pre-training knowledge, and you're given just a little bit of a context, what just happened. So essentially, there's no up-to-date perception of the new world, and there's no continuous episodic memory. Okay? And this is just one little piece why it doesn't feel like a real experience from today's AI models. And imagine what learning looks like in a real-world embodied agent. Okay? So you'll have to quickly adapt to new environments and learn in the open world. You encounter new concepts, new tasks, and new goals. You take actions and learn from these new observations. And essentially, your memory form new representations of perceiving the world. These representations change as you do the exploration. So you might be wondering, okay, why can't we just learn everything in a big static AI model, right? So I think this is a great question to wonder about. And Rich Sutton has, put out this big world hypothesis, right? Which is essentially saying that the AI models that we build, the AI agents, can never fully perceive, model, or learn the optimal solution to the entire world. The world is big, it's dynamic, and you really have to have an AI agent that's domain general, that's experiential, and that's open-ended. Okay? So instead of put all possible offline data and pack it into this freighter ship, okay? In contrast, the always learning agents just have to learn the current tasks very well. Okay, so this is what I'm going to talk about today, the always learning machine for embodied AI. And the existing paradigm also trains AIs or potentially embodied AIs, but they train from all kinds of internet data with stage-wise pre-training. You model, say, perception stages, planning stages separately, and you do a lot of offline pre-training and human demonstrations. And instead, the always learning machine will learn the representation in a closed loop. It will do the perception and then transfer them into memory with high-level abstractions, and then do the planning, and then take actions from your plans. The actions will lead to new explorations, which leads to new observations that forms your new representations. So everything is performing perception and action in a closed loop, and then also learning the representation from there. And you might also wonder, why not doing reinforcement learning? What about RL? Where's RL in this picture? Okay? So similarly, RL also performs learning in an agentic environment. But what's different is that RL deals with the classic ones only deal with the exogenous objectives, which is, for example, the agent's survival and the extrinsic rewards, whether or not you have reached the goal or not by some extrinsic definitions. But I think there is a lot more to be done in terms of the endogenous objectives of the agents, right? How do we learn the representations without even having an external rewards? So what are these endogenous learning objectives? Well, first of all, in terms of the perception and memory, you could do the next latent prediction, as has been done in self-supervised learning in JEPA world models. And in terms of planning, you can do the planning in your latent space and, for example, do the latent goal reaching. And lastly, for exploration, you can form your intrinsic reward rather than let the external world tell you where to reach. And this leads to latent discovery. So I'm going to talk about what are the challenges. And as it goes, challenges also come with opportunities. So first of all, in the always learning paradigm, you will have to have the physical grounding, right? But these can also give you spatial temporal continuity as additional teaching signals that you wouldn't otherwise have with, say, static images on the internet. Secondly, there's very strong temporal correlations in these embodied videos, but on the other hand, you will get coherent episodic memory rather than something scattered like single sentence or a single piece of image. And if you're doing always learning, the continual learning will be a question here, right? Because you're optimizing towards the continuously moving target. But the benefit, the potential opportunity is that you may generalize to your current task better because you're optimizing to the current task rather than a collection of all the other tasks that are potentially irrelevant. And also, as you're changing the weights of the model in real time, you may find out you can collapse at the deployment. Maybe the learning objective isn't set up correctly. Maybe there is some collapsing mode in the model. So this is definitely one of the other challenges. But on the other hand, it allows you, the model, to explore the creative frontier. You can always create new things and add it to the collection of the experience of the model, whereas the offline trained model wouldn't have the same capability. So let me start out with introducing some of the work that our lab has done in these directions. So first of all, I'd like to talk about learning the high-level cognition and motion recognition. Okay? And this is a little timeline that the human brain, the babies, started to develop visual understanding in their early ages. So as soon as the 3rd month to the 6th month, first half a year, babies start to recognize objects with their object permanence and also recognizing moving objects very well. Okay? So it seems like these two capabilities doesn't give you all the way at the beginning, but start to emerge around the same time, same period of the life. So we are start wondering whether we could enable these two types of understanding, the object recognition and motion understanding, jointly in one model that learns to perceive the world. Well, standard self-supervised learning tries to throw out the motion information, try to map different views of the same object to the latent space, whereas action condition world model requires some external actions. What we would like to do is to model the motion or the transformation between the two adjacent frames as latent variables, so that once we have inferred these latent motion, we would be able to predict what comes up next very well. So we're interested in building these latent motion models. And on the other hand, we're also inspired by the classic computer vision model, which tries to estimate motion, aka optical flow. But in these classic models, they try to explicitly reason about motion in terms of the change in the XY coordinates, which we think is maybe a too rigid of a representation to represent motion. And we're interested instead to represent them in the latent space. But we took inspiration of how to build these models where we have these top-down hierarchies of having the very high-level motion information in the very top and gradually refine them layer over layer and try to predict, using the latent motion variable to predict what comes up next in the intermediate layer of the next frame. So the objectives is laid out in a hierarchical manner, right, instead of just on the very top. And here is a little video showing you what kind of representation we're able to get by just doing unsupervised learning from self-driving videos, which is a form of embodied experience. And so you can see we can get very good semantic understanding. So this is a readout, probing results by using the representations. And so these are the semantic understanding. And what about motion? So we also try to evaluate the tracking and optical flow. And in both cases, we're able to achieve very nice results by only doing self-supervised, unsupervised learning from videos. So next up, we want to move this one step further, which is further restricting the data that we use for learning. So what is it like to gain visual understanding from a baby-like experience? Okay. So what we were trying to do is streaming visual learning. So previously we took a video and chop them up into consecutive frames and then do the unsupervised learning. So now we're going to do a continual streaming style. We will stream the video once in a lifetime, and we start out with a randomly initialized network and then end up with a trained model, just like how baby sees the world with once in a lifetime. And we took egocentric video data sets that's about 200 hours from one single participant, one baby, over the course of 2.5 years. Let's see how far we can push down this road of streaming video learning. And one key question is, can we leverage the temporal continuity that's given from this data source, which is, I think, one of the opportunities that we can benefit from. And one insight we're trying to push is, can we leverage the events that happen in this video, not just at the frame level, but try to cluster or group them in a higher level concept, such as the events or the key moments. So for example, the baby might be experiencing a reading event with their parents, and then watching their parents typing on computer, and then maybe then playing some toys in their own room. And these contents will get stored and grouped them in the memory, and they may get replayed and consolidated later when we try to learn the representations. So the research question here is, can event concept emerge and benefit streaming representation? Okay. So the answer is yes to both questions. The events concept can emerge even though the network has been completely trained from scratch. Over time, the events are getting better and better, and then we can also use these event boundaries to help the representation learning. So here is what it looks like in the algorithm that we designed. So we start out with a video. We're going to encode them with our encoder, and then we tried our best to cluster them into consecutive clips. Okay? And then we're going to group them further into non-consecutive segments. And these events will be first processing a short-term memory where we look at which frames are belonging together. And then we're going to store them in a longer-term memory, which is being used for replay when we watch the new video segments. It probably can remind us of something that happened in the past. Okay, so this is a two-tier memory system that's supporting this streaming and continual learning process. And so here is what we've done in the experiments. We took two data sets. One is the baby video data set that I just introduced, and the other is called Krishna Cam, which is collected by a grad student. So it's a different type of experience, but also egocentric. And so what we're looking at is the streaming learning performance of various kinds of continual learning models that doesn't consider the video as a temporally continuous data stream, which only consider them as a separate static frames. And also the i.i.d. performance, which is just randomly sampling from the whole video stream as if they are just separate images. And interestingly, our method is getting the best performance, and this is try to probe for the classification as well as the object detection performance from the trained encoder. So see how much representation they can gain from there, okay? And we're also compared to other prior work that treat the video as equal uniform segments, and of course the clustering helps it better. And here is what it looks like when the network is just being initialized. Of course, you can still get some similarities by comparing different frames. And after the training, you get better and better event concepts just because the features are getting better so that when you group them based on the similarity of their latent space, you'll get getting better event concepts. And you can also merge the events that are non-consecutive. For example, here is a person, likely the parents of the baby, sitting beside the desk, and you can see the same scene happens multiple times in the lifelong experience. And more recently, we pushed this even further, multimodal learning from the baby's lifelong video stream. And so what we did was transcribing the audio as well, and then doing the multimodal associative learning between the text and the video segments. Okay? So there are three different learning objectives: the image level, which I just introduced about, and the multimodal segments, which represents the video segments of where that text happened, okay? And also the temporal segments, which is the event concepts that's appeared in the previous algorithm. And so here are some of the experiment results. So we're comparing promisingly to the offline algorithm. So the first bar is kind of like upper bound because it trains for 300 epochs, whereas the second bar is a compute-matched experiments of i.i.d. learning, which means that you take the same number of gradient descent steps as our streaming algorithm, which doesn't look back when training. So we're kind of getting closer in terms of closing the gap. And here are some visualizations to see whether the learned encoder gets a proper representation associating the words and ground them into different pixels. So, from a baby-like experience, the network starting to gain the concept of what is a cat and what's a ball simply by listening to what their parents said to them in the video. So here, just to give you a recap on the agenda, we covered learning perception in a streaming video experience and also how to group them in the memory, associating them in the words. And next time, I'm going to talk a little bit about doing planning and exploration to kind of complete this closed loop cycle. So now with a good latent space that we just learned from watching videos, one thing that you could do as a downstream task, other than just doing object detection or classification, is that you can actually do some planning with the latent space. So this paradigm is called latent world models and model predictive control, which has been developed over the last few years following this JEPA paradigm, where you embed your current observations in the latent space and try to minimize the latent distance towards the embedding of the goal state. Okay, so you can do some planning with your action condition world model and trying to minimize that overall distance to the goal. So what we're trying to do here is, always learning. So we try to, kind of adapt this encoder and predictor of this world model every single observation that comes into the agent. And this idea of adaptive and model predictive control isn't new. It actually has been pursued in the control literature and neuroscience literature for decades. But I guess what's new here is that we're also adapting the entire model with a latent space representation, whereas the past literature mostly adapts in the dynamic space. So in the latent space, we have to continuously ground the encoder and get it to be corrected, because if your predictor has some error in the latent space, the error can amplify over multiple steps, and which can lead to lowering your planning success. And so this is a recent work called ADA-JEPA, which is Adaptive JEPA World Model. The idea is very simple. So we try to, at test time, adapt our encoder and predictor in a closed loop, right? So we take, using a world model, make a plan here in the latent space, and we take the action that optimizes the plan, right, in the real world, and then we take a new observation and compare that with our predicted rollouts. And of course, there is some predictive errors. We're going to adapt our encoder, predictor, everything in our model by minimizing that predictive errors. And then we do replan again to take the next step. Okay, so there's a very simple idea, making the world model more adaptive and minimizing latent prediction error. And every closed loop step, we're also just making one gradient step on the encoder and the predictor, so that we are not taking too much overhead, making the whole thing adaptive. So here are some results. These are toy embodied environments. The goal is to move this piece, the little toy block, to the target location. And here we are seeing the success rate over time, where the dashed line is the frozen model that's non-adaptive. So they kind of stuck in the middle because of this prediction errors, even though some of the shapes have been trained with thousands of trajectories. And the solid lines are our adaptive JEPA world model planning. It gets much better in terms of planning success. And I'd like to share this one plot for training data efficiency, which I found very interesting. Where here we're kind of scaling the number of trajectories and number of shapes that we train the model. So typically you would expect, like scale the offline pre-training data, but definitely leads to some improvement, and this is indeed the case. But if you look at the lines over here, which is the adaptive ones, even if you train with, say, just 1,000 trajectories, right, with a single shape that's about this current task, what this shape is about, it actually outperforms an offline model that has seen like 64,000 trajectories, which is great because now this proves that this adaptive learning paradigm has the potential of saving a lot of more training data if you only care about optimizing the current task. So here is a little bit of a pivot towards the last part of my talk, which is more about the exploration, which is the final piece of this closed loop learning. So always learning embodied agents, right, learn from the observations that are caused by their prior actions. Okay? So the action matters not only for optimizing the agent's short-term goal, which is probably reaching an object in a few seconds later, but also the long-term learning of the knowledge and representations. Okay, so this is a notoriously hard problem in reinforcement learning because this long-term credit assignment problem is hard. And here what we need is creative exploration, which help us build representations while interacting with the world. Okay, but before approaching to this question, the question is really, what is creativity fundamentally? So here is kind of a mental picture of understanding creativity. Some people say it's about novelty, but I think it's only half of the puzzle, right? So novelty is not enough for creativity. You can have a randomly generated white noise that has zero meaning to you, but is absolutely novel to that hasn't seen before in this world. Okay, so essentially what you want for creativity is something that's initially unfamiliar to you, but can be quickly understandable through some rapid learning. So if you think of this manifold containing a lot of existing concepts that you understand very well, creativity is kind of lying on the boundary that's not part of your existing concepts, but can be quickly absorbed by expanding this frontier of understanding. And I should say that, so this notion is also deeply related to prior literature. For example, from Schmidhuber in 2010, he proposed using compression progress as a notion of creativity, which is more of on the pure theoretical side. And more recently, on epiplexity, which is trying to measure the structure of data. And here, what I'm going to tell you later is more of an instantiation of this creativity notion in a meta-learning framework. But to summarize this slide, what I'm trying to say is creativity is deeply bound to the past experience of the agent. So there's no objective notion of creativity. So the frontier of the understanding of the subjective agent's subjective representation slowly expands so that it keep continuously absorb the creative concepts. So this is a recent project. We didn't touch upon the embodied aspects, which we're just trying to do more of an image generation experiments. And here is a model on what I call the creator-appraiser meta-learning. So the creator tries to create some artifact and present it to the appraiser. And the appraiser internally tries to understand what's going on by minimizing some inner objectives. So this can be auto-encoding by doing reconstruction about this input, or can be other objectives that I'll talk about later. And the creator's goal is to maximize the learning progress of the appraiser within a few steps, so that it appears initially very unfamiliar and perplexing to the appraiser, but only after a few steps it can be rapidly learned. So here are some very toy experiments I trained on MNIST, which the model, both the creator and appraiser have only seen MNIST digits, which is 0 to 9 handwritten digits in their entire life. And here the appraiser is simply an autoencoder, try to reconstruct the image. Okay, so if you use a diffusion model and not guiding it, just doing unconditional sampling, you will get digits really look like 0 to 9, nothing very interesting here. And if you introduce this appraiser and ask the creator to maximize the surprise and learning progress, you will get some very interesting handwritten-like characters that at least I haven't seen before, but sometimes looks like different components of the digits. So that's very interesting. So now let's move to natural images. And what I used here is a stable diffusion generator and a clip appraiser. So the clip appraiser tries to maximize the cosine similarity between the image and the text internally in its learning objective. And what's important here is that I'm using the same prompt for every single image. This is a photo of something. Right? I'm not trying to be creative in the language space, but the creator is trying to optimize the latent embedding of this whole sentence through the learning process, so that it might be implicitly finding some creative prompts, but I'm not actively looking for them in the raw language tokens. And here are some samples. So if you sample from stable diffusion model, they're just like, this is a photo of a lion. It's always a lion that looks like a photo that you took on the African safari. And also this flower photo is always similar if you sample from this prompt, I guess. But once we introduce the appraiser, it gets very interesting. This one looks like an autumn leaf with a side face that you almost never see when you do the regular generation. And I like to zoom in here. This flower was very interesting to me because, the center looks like an egg yolk rather than a regular flower. And all the edges are kind of rectangular, not like kind of the regular natural shape of the flower. And this one gets even a little bit more black and white and abstract space. And so far this piece of work handles more on the image generation side, but I thought it's potentially a nice direction towards creative exploration in different modalities. To sum up, so here I introduced this direction of always learning machine from embodied experience. And it has many components in there in a closed loop: the perception, memory, planning, and exploration. And importantly, we try to define the endogenous learning objectives that shape the latent representations throughout this closed loop. And to close up, I'd like to also say there are many open questions in this paradigm, and so far we haven't solved at all. And so first of all, like once you do this always learning, adapting the parameters in a closed loop, how do you form the episodic memory? Right? So maybe there's another way than just stacking up the tokens in a sequence. Maybe the gradient descent process gives you some time ordering awareness. And this is also another topic that I was planning to talk about in today's talk, but I found they can't fit in the slides. It's more about the self model versus the world model. So as the agent try to model the world, maybe it's also in parallel trying to model the agent itself. And there's also the stability versus plasticity problem that has been a classic problem forever in continual learning. So what do we retain in our representation? What do we like throw away and then learn new representations? How do we control this balance and trade-off? And perhaps there's meta-level controls. Maybe like the agents could control what can be learned, in this embodied experience. Maybe I see some, like maybe I enter a blackout room, and then maybe I tell myself I don't learn from the lack of experience at all, right? Because it could potentially lead to collapse of my my representations. And perhaps the agent could form latent goals by trying to plan out, more longer horizon goals and then forming its own latent intentions and goals. And there's also the exogenous versus endogenous gap. Like, for example, the RL is probably the ultimate solution, but what kind of outer level objectives will lead to this inner level representation learning objectives? And are they equivalent, or can we find things that are more equivalent than, two completely separate paradigms? And with that, I'd like to acknowledge, my amazing students who contribute to the work, and also the funding agencies, and especially the Global AI Frontier Lab, which fund a portion of the research I presented today. Thank you very much.
Thank you, Mengye, for your excellent presentation. We now have time for a few questions from the audience. If you have a question, please raise your hand, and a staff member will bring you a microphone. Any questions from the audience? So let me start up a question. Thank you for your excellent presentation. It was very motivating. The concept that you mentioned about episodic memory, I was wondering, it seems like inspired by the human recognition or understanding. Some of the episodes people memorize forever, like from the entire life, even seeing at once. But sometimes other type of episodes you keep forget, even though you saw it many times. What do you think the main reason, like, do you see similar behavior in the neural networks or AI models? Similar thing happens, or if you saw some similar episode observations, what is your insight? Why these things happen, and how you can overcome these issues?
Yeah, I think it's a fascinating question. I don't have like a full answer to it, but I think one of the driving principle is that these agents are doing error prediction, error minimization in this predictive process. So if there is a larger surprise in terms of the error prediction, it makes sense for them to store these surprisal moments for longer term. But I should say there's also other types of meta-level controls where I control where I kind of snapshot the current moment for it to memorize in the longer term. And also the human memory is oftentimes associative, meaning that it stores many moments, but it's just that we don't retrieve them unconditionally. We kind of need some conditioning in the cues to be able to retrieve them. So we also study like in multimodal learning, what's the best replay strategy? When I see this chair, maybe it reminds me of some other chairs that's semantically relevant, but maybe providing different shapes and content. And this could potentially help multimodal learnings. And this also an area of our interest.
Right, thank you. Some other questions from the audience? Yeah.
Thank you for the great talk. I'm a neuroscientist, so I was mostly intrigued by you mentioning the coincidence between co-occurrence of the movement of baby with visual development. I was wondering, there is certain brain functions, like visual functions, that can be developed even without any visual stimuli, visual experiences. So whether you could give your thought about like how those priors can be implemented in the AI models, And then second, there is also like critical period in the development of babies, and then how that could be also used to improve the I don't know, like AI more brain-like.
Yep. Thanks for the question. Yeah. So I'm not a neuroscientist, so I will give my 2 cents on the question that you just asked. So one of the things that we are currently very interested in studying is how can we leverage some synthetic visual stimulus. For example, this is inspired by works in these retinal waves, which happened, even before birth of the baby. They start to synthesize these retinal stimulus, and we thought that could be a good source of doing pre-training for the networks to gain these, primal kind of motion awareness. So this is one piece of insight. And the other is about the critical period, which I think could also very much align with the neural network training. There's a phase where the errors get decreased by a lot, and then later in the fine-tuning or post-training stage, you don't get to change the representation so much. It's more like in locally in a basin in the lost landscape. But these are very hand-wavy, high-level sort of associations of different concepts. So I don't try to make a claim on the strong connections.
I think we have a few more moments for our last question. Any question from audience? All right. I will finish with my last question then. Since it is a multimodal AI, what do you believe, other than you talked about the retina waves, but what type of other modalities do you think could be incorporated in always learning paradigm?
Yeah, I think it depends on what type of agents that you like to build and what kind of sensory experience we have. I think audio definitely makes a lot of sense, right? I think perhaps touch or maybe sometimes smell, can be additional source of information that are very good. And yeah, I think having all these in an embodied agent will be a very exciting direction for multimodal AI. Yeah.
Okay, thank you. Thank you once again for your insightful presentation. Please give him one round of applause. Thank you.